Back with another seminar. And today we have Nur talking about bridging the empirical and theoretical gap in neural network formal language learning using the minimum description length. So we'll have questions at the end, and the recording will be put up on YouTube after, along with the slides, the paper, GitHub, anything else. So thank you. Take it away.
Hi, everyone. Thank you, Marco. Someone started apparently demolishing the building just right now, so I apologize in advance for the horrible noise. I hope you can hear me nevertheless. So I'm Noor. I'll be presenting joint work with my two advisors, Emmanuel Shemra and Ronnie Katsir. And today's talk will be about a mystery that has been out there for a while now, and the mystery is the following. We've known for a while now that neural networks are able to reach perfect solutions to some problems in some domains, at least. We'll be interested in formal language learning tasks. And even though we know that these perfect solutions exist somewhere in the search space, nevertheless, we know that we never find these solutions to these problems. So today's talk would be about how we might reach these perfect targets nevertheless. And I'll try to argue that in order to reach these targets, we may need to change something fundamental about the way we train these networks, and specifically the objective function that we use in order to train them. So what do we know that neural networks can do? So we've known since Ziegelman and Sontag, 1992, that recurrent neural networks, at least, are Turing complete. This is a very strong result that is based on two very strong assumptions. One is that we need to have infinite precision in the activations of the network, and another is that we need to have an unbounded runtime of the network, which is essentially the runtime of the Turing machine that we're emulating using the network. So this is a strong finding, but it's also impractical for any real-life application. So in recent years, we've had a growing list of works that have looked at what neural networks can do in practical settings, namely finite precision and bounded runtime, often real time. So today I will focus on one very nice result by Weiss and colleagues from 2018, who showed that LSTMs and also L-man RNNs with ReLU activations can count. They can hold real-time counting configurations in their weights. And as such, they can, in theory at least, learn and recognize a family of languages called counter languages that include languages like A to the N, B to the N, and Dyck1. So this is in theory. What about in practice? So empirical work in this domain usually looks like this. You take a model, a network, you take a formal language, and since we're working with formal languages, we can very easily generate the training and test set in different sizes. So usually the train set is relatively small, and the test set tests the network on strings often in length longer than what was seen during training, or sometimes also depth when relevant. And success on such tests was usually, in some works, enough in order to conclude that the language was learned by the model. Only that if you look a bit more closely at these works, you see that things aren't as clear as we would have wanted. So these works usually fall into one of two categories. Either people report what happens after this last test value, and often this is a failure, or people just don't report what happens afterwards. So in this talk, I will try to focus on what we want to happen after this last point of test, and how we can make sure that networks generalize perfectly after this last value. So common to all, so I'll present today three works that we completed in the last couple of years. The table that we just saw is taken from our paper from last year, in which we provide a summary of previous works in the field, and also provide provide a standard benchmark in order to test the generalization capabilities of networks in a standard way on formal language learning. And in the rest of the talk, I will discuss two papers. One is our TACL paper from 2 years ago, in which Michal Geyer also participated. And the third one that we completed recently this year. And common to all these works is our proposal to apply the minimum description length principle to neural networks in order to get them to generalize well and sometimes even perfectly well. So very briefly, the MDL principle and minimum description length principle says the following. In order to find a model, in our case, a network, we can also call it a hypothesis, that balances generalization and data fit well, we need to find a model that minimizes the following sum. So on the left, we have a term that basically in some situations, for example, in probabilistic situations, amounts to the standard loss function that we usually have. So for example, the cross entropy loss or surprisal. And on the right, we have a term that corresponds to the encoding length of the model itself. If we only minimize the term on the left, which is the standard loss often, we end up with an overfitting model. If we only minimize the term on the right, we end up with a degenerate model that doesn't learn anything and is simply void. The assumption in the MDL principle is that if we minimize both terms at the same time, we should end up with a very good compromise between a generalization and data fit. So we'll be dealing with recurrent neural networks. So for RNNs, the MDL principle will look like this. So again, on the left, we have the standard loss function, which in our case is the cross entropy loss that we want to minimize at the same time with the encoding length of the architecture itself. So this would include all connections, all weights, and specifying exactly using a very specific encoding scheme how to encode the network and to be able to recover it from this encoding later on. Moving to the MDL objective leaves us with a non-differentiable loss. So we can no longer use backprop. Instead, we use just as a default a genetic algorithm in which architectures compete for survival based on their MDL scores. So a genetic algorithm or an evolutionary algorithm is basically just a competition within a population of networks in this case that compete based on their fitness, which in this case is the MDL score. So we try to keep the mutations that networks go through as simple, as agnostic as possible to the problem that we're trying to solve. So the mutations are very simple. We can add or remove a unit. We can add or remove a connection. We can mutate the activation functions for each unit, and we can mutate the weights or the biases. And this is how it looks. So the model starts with a random and empty network that doesn't contain any hidden units. This is a sped up version of the evolution of the winning A to the N, B to the N network that we'll see in a few slides. So what we see is that the model starts with a network that doesn't perform very well and very quickly picks up on something that works and adds some units. And very quickly it reaches 100% test accuracy. And the nice thing to see is that you can actually see throughout the evolution of the network, the two terms of the MDL score in interplay. So at the start, we see that the model sort of overfits by adding units, and then it starts pruning them. And this is the pressure that comes from the right term that has pressure for simplicity in the architecture. So let's look at some results. We started with some sanity checks to see how the model behaves on very simple tasks. So the first task is the echo task, in which we simply need to echo the input in binary that the model gets. And the result network is here on the right. As you can see, it's very simple to read and transparent. So just a quick walkthrough on how to read this. The yellow unit is the input unit, the blue is the output unit, and what you see is just a single connection with weight 1 that was evolved in order to simply copy the input to the output. And as simple as this task looks, so actually standard RNNs don't perform as well. So just as an exercise, try to imagine how a standard RNN cell for this task would look. It wouldn't be as simple as and as a transparent. And also once the RNN reaches a certain size, it would simply memorize this input instead of generalizing to this very simple echo function. The next simplest task is repeat the previous step task, in which we simply need to evolve some kind of memory in order to remember the last step and output it at the right time step. So here as well, the following network was found, which is very simple and almost identical to the previous one, only that here the dashed line represents a recurrent connection, which basically says copy the value of this unit from the previous time step into this unit. Here again, as simple as it looks, standard RNNs, once they reach a very basic size, don't perform as well on this task. Let's move on to some more interesting results. So we tested the model on A to the N, B to the N. We tested on 500 sequences sampled from a PCFG for this language. And the model found this network. Here we allowed ourselves to use non-standard activations since we're no longer limited to a differentiable search, to a gradient-based search. So we allowed ourselves functions like the step function. In this case, this was used. And as you can see on the right, a very simple network was found that has only one hidden unit. And the way to read this is sort of like an automaton rather than a standard way to visualize RNN cells. And what's nice to see here is that you can very clearly and easily see that the network has found the counting solution by simply creating this recurrent connection from the hidden unit onto itself. And this is basically the counter that counts the number of A's and balances it later with the number of B's. Since the resulting network is so small and transparent, we were able to provide these nice walkthroughs in the paper that show that the network is actually correct for any input. And as far as we know, this is the first A to the N, B to the N network for which this was possible as sort of a formal proof to show that the network is correct for any input. We also tested a bunch of standard RNNs on the task, and while it looks like they reached a very high accuracy score, this accuracy score actually hides an important detail, which is that the network can reach such a high score only by guessing B's, for example. This is because we test the networks on what we call deterministic accuracy, which is measured at the deterministic parts of the string. In the case of A to the N, B to the N, this is the part after once the first B appears until the end of sequence. So even if you have a very degenerate model that only guesses B's but doesn't get the end of sequence symbol correctly, it would still reach this very high accuracy score. So reaching 100% accuracy here is important. Another way to visualize the network's mechanics is to visualize the output probabilities that the network.
I'm sorry, I have a clarification question. I thought this model was trying to classify whether a sequence is in AN, BN, not generate. So what do you mean by predicting the end of sequence or predicting an B?
So it's not a classifier. Thanks for the question. It's not a classifier, it's a language modeling setting. So the task of the network at each time step is to predict the next symbol. So
how do you expect it to be accurate on the A part of the sequence?
So we don't measure accuracy on the A part. We measure accuracy as what we call deterministic accuracy, which is defined only on the deterministic part of the string that starts once you see the first B and includes the last B where you need to predict the end of sequence symbol. So that would
Got it.
be
Thanks.
starting here. But thanks. So another way to visualize what the network is doing is by looking at the output probabilities. So this relates to Yuval's question. So here it's visible that the network was trained, that the model was trained on a training set that didn't contain the empty strings. So it learned that for the start of sequence symbol, it always predicts A's and A with 100% probability. And then as long as it sees A's, the network knows that this is the non-deterministic phase of the string. So it predicts the correct probabilities for A's and B's. This is the probabilities induced by the PCFG that we used for the training set. And then it's very easy to see that once it sees the first B's, it goes into this deterministic phase, predicting only B's until the last B where it predicts the end of sequence symbol. If you're more used to looking at RNN cells this way, so this is the typical way you would visualize such a cell. And this is a network that we trained without the non-standard activations. So this uses only standard ReLU and TAN-H units. And this network is equally successful. So this reaches 100% accuracy on at least n equals 10,000. And we also have PyTorch versions for such perfect networks for A to the n, B to the n, A to the n, B to the m, C to the n plus m, and Dyck 1. Skipping a bunch of languages that were learned well and are available in the paper in order to reach some more interesting discussions. So we also tested the model on the Dyck family of languages. So this family is interesting because for D1, we know that this is still a counter language that can be recognized using only a single counter. But for D2 onwards, we know that a fully operational stack is needed in order to recognize these strings in the general case for any depth. So this task is a good test case for the model because we already know that the model can evolve counters, but we want to know whether the model can also evolve more complicated representations. So we started with D1. As impressive as this is not surprising at this point because we already saw that the model evolved the counter for A to the n, B to the n, and this is what we see here as well. So again, a very small RNN cell and very transparent with this very visible counting mechanism. And here again, the network is transparent and small, so we can provide this walkthrough that explains why the network is correct for any string in the language. And here again, the other RNNs that we tested crash actually. And here again, the output probability is also visualized that the network is doing the right thing. So we see these columns with blue end of sequence probabilities that show that the network knows that as long as the brackets are balanced or as long as no bracket was opened, it needs to predict the end of sequence or the opening bracket with the probabilities that match the CFG that we used. And as long as you have open brackets, the network correctly predicts the right probabilities for a closing or a new opening bracket. So this is D1. What about D2? So again, for D2, we need a fully operational stack in order to recognize the language in the general case. So anticipating that for this task, the model would need to build in a lot more into the architecture, we trained on many more sequences, on 20,000 D2 sequences. And the model performs well. It reaches 99.3% accuracy. The competing RNNs also did well, but not as well. But it doesn't reach 100% accuracy on the test, which is very large. It does perfectly well on strings that have up to depth 4. But once you look at what happens with strings with depth larger than 4, you see that the model actually uses all kinds of heuristics in order to get this right. So you have some recency effects, and you have all kinds of things that reveal that the model doesn't actually solve this in a general way. So at this point, we asked how come the search doesn't find such a fully general stack solution to the problem. So in order to know whether the problem is even available in the search space for the search, we built a manual network that implements a stack for this task. So this is very similar to the construction in Ziegelman and Sontag. Only here we made our lives a bit easier by using non-differentiable units such as moduli 3 and the floor function. But basically, the idea is very similar. You push and pop into a value of one of the units, and we could show using this network that such a network exists in the search space and that it's 100% accurate for any string in D2. And more importantly, what we could do is measure the MDL score for this network and figure out whether this network has a better MDL score compared to the network that was found here in practice through the search. And indeed, this network has a better MDL score for this training set at least, which means that in a perfect world with a perfect search, we should have found this such a network or even something better. This was built manually, so in theory, this can be maybe improved by a good search. So the question remains, how come this network wasn't found by the search? So we don't know for sure, but one hypothesis that we have is that this network is surrounded by an evolutionary moat. So let me explain. This network was built manually, and this means that it's enough to remove most of these connections or change one of the weights or remove some units in order for the network to become completely non-functional. This means that a search would need to really look into the future and jump over a lot of hurdles of non-functioning networks in order to reach such a network. In other words, this network seems to be surrounded by some moat in the search space. Nevertheless, this shows that the problem here is a problem with the search rather than with the objective, and that if we had a better search for this objective, we should have found such a network for this task. And one last task that we tried, here we leave the language modeling setting and move to a very basic task of general addition. So we model it as feeding a network with binary digits of two numbers. We feed from the least significant bit to the most significant one. And as far as we know, no network that was trained using standard gradient descent methods reaches perfect performance on this task, as far as we know. So we trained the model on all pairs of numbers from 0 to 20, and we tested on a huge test set of all the subsequent unseen pairs. And the following network was found. And here again, it's very nice to see what the network looks like. And it's actually also visible that the network has some kind of carryover mechanism that is visible here in this recurrent and then feed forward cycle. And here again, since this network is very small and transparent, we can provide this walkthrough that shows that it's actually correct for any two numbers. Okay, so this was part one. In the last part of the talk, I'll try to explain how come these MDL results look so good. So as a reminder, the MDL objective says the following. We want to find a model that balances, that offers a good compromise between simplicity and accuracy. So the term on the left, again, represents the typical error. And if we minimize it, we get an overfitting model. And the term on the right can be taken as some kind of penalization on complexity, forcing the model to be as simple as possible, given the other constraint. So the idea that we want to penalize complexity and prefer simplicity is not unique to MDL, and it appears also elsewhere in all kinds of objectives. And the two most common ones are the following regularization terms that people usually add to the objective in order to penalize complexity in the model. And these are the L1 and L2 norms. The idea is very similar. In L1, we add the sum of the absolute values of all weights, and in L2, we add similarly the sum of the squares of all weights. And the idea behind these two regularization techniques is the same. We want to penalize complexity by through an assumption that equates simplicity with the magnitude of the weights themselves. And the assumption is that if we have large weights, the model prefers some kind of input or output and learns to overfit some kind of value. And if we keep them small, the model won't overfit in this way. It will keep its preferences simple in a way. The problem with this is that a smaller value doesn't necessarily mean that it's simpler. So just as an illustration, let's agree that we're in a universe where the value 1 is simple. And we can immediately see that values more than 1 aren't necessarily simpler than this value. So again, as an illustration, let's say that the training data were sampled in some way that was a bit biased, and we have some sampling artifact. And the network can assign some very specific value that is smaller than 1 in order to adhere to in order to output some very specific probability to a very specific class. An even more extreme example is going back to Ziegelman and Sontag, the construction of a binary stack that is encoded in a rational that is smaller than 1. So here again, we see that we can stuff a lot of information inside a value that is considerably smaller than 1. So if there's one take-home message from this talk is this: information finds a way. If you have a good enough search, your model would find a way to smuggle information even inside these very small values. And if you want to avoid it, you need to very explicitly penalize information content in the weights or in whatever parameters you have in the model. And the reason this is done better in the MDL networks is because we don't equate scalar magnitude with information content in the encoding that we use in order to encode the networks. What we use is a simple but slightly better encoding for the weights that works like this. We represent a weight as a rational fraction. And then we encode each component, the numerator and the denominator, as a bit string. Doing it this way actually penalizes very specific values. And if you take, for example, the values that we see here, these would get much longer, significantly longer encoding lengths compared to, for example, to simple values such as 1 or even 2 or half. You can try it yourselves. So one last test case that we tried in our recent work was to see whether the MDL principle also transfers well to other architectures. So in the TACL paper, we used these free-form RNN cells. Here we want to see whether this applies to other architectures, namely LSTM. So going back to the result by Weiss 2018, we know that in theory, LSTMs can implement counting. So they should recognize languages such as A to the N, B to the N. Nevertheless, we also know that no such perfect LSTM for A to the N, B to the N, or other counter languages was ever found, as far as we know. That is using standard techniques. And these networks usually fail at very low values around this area. So what we did was we used the general instructions provided in WISE in order to build such a counting LSTM manually. And doing so, we could do several things. So first of all, we started by comparing this manual network with a network that was trained organically using backprop. So we ran a large grid search, and we took the best one based on validation loss. And here we see, we started by inspecting the behavior of the two networks. So we started by plotting the memory content of the two networks. So what we see here is the plot representing each component in the size 3 hidden vector of the LSTM. So what you see on the left is the hidden vector of the manual, or we call it the golden network LSTM. And so naturally you see that it counts well. It uses only one component in order to keep the counter as it should. And we keep the other two components constant for calculations downstream. On the right, you see the same thing for the backprop trained network. And you see that the network has learned to count relatively well. You see the counter, one component of the hidden vector that seems to hold the counter count up until the correct value, and then it starts going down. Here I'm plotting for n equals 73, which was the first point of failure of the trained network. So what we seem to see here is that the counter seems to go off at some point and seems to go below 0 at some point. And you also see that the network isn't as precipitous as the golden one and uses its two other components to store some other stuff that we're not sure about. The fact that the network is imperfect becomes visible when we plot the output probabilities of its network. So for the golden network, we see that similarly to the previous ones, the network outputs the correct probabilities at each phase of the string. And for the best backprop train network, we see that it's imperfect in two ways. One, I hope you can see that on Zoom, the output probabilities for the low end values seem to fluctuate in the beginning. And this probably represents the fact that the network slightly overfits the more common low n values, since the PCFG that generates the training set induces a power law in the n values. And more crucially, we see proof that the counter in the network does leak in some way. And we see that the network outputs the majority probability to the end of sequence symbol one step before the last one. So similarly to the findings in WISE 2018, the network starts accepting at n equals 73 strings from the language a to the n, b to the n minus 1. Another thing that we could do thanks to the golden network is to see how the loss surfaces around both networks look like. So here we see the loss surfaces around the golden network for all three loss plus regularization terms. So we have cross entropy plus L1 plus L2 and plus the encoding length of H, which amounts to the full MDL objective. And what we see that at least in this area of the golden network, if we trained using these losses, we would end up with very imperfect and partial networks for this task. So L1 would actually run the network into the ground by probably setting everything to 0 and reaching 0 accuracy, which probably means that this minimum point represents a network that only outputs A's, for example. L2 does slightly better in this area, but still ends up with a suboptimal network. And the pink and light blue check marks only coincide for the full MDL score, which means that the minimum and the golden network only are the same only for this objective. If you're a L1 or L2 practitioner, we also have an exhaustive table with more lambda values for the actual score. And whatever lambda value that we used, we ended up with these imperfect solutions. We did the same thing only for the best backprop train network. Here we plot in 3D because we also want to see where the plane of the golden network lies, since the network lies in a different area of the search space. So the yellow point is the best train network in the center. And the first thing you notice is that as expected, the training ends up with a network that lies in these smooth and convex areas of the search space. And here again, we see that if we trained using L1 or L2, we would end up with these far from perfect networks that actually go below the value that was actually needed in order to get the golden network. While if we trained using MDL, first of all, if we plot the loss space for MDL, we see that in terms of MDL, the train network ended up in a rather friendly zone of the MDL search space, smooth and seemingly convex, but didn't go low enough in order to reach the MDL level of the actual golden network. So in other words, it ended up in a local minimum in terms of MDL. And one other thing that we did was plot the regularization surfaces around the different regularization terms. So for L1, L2, and the encoding length. And what we see as expected is that L1 and L2 are very smooth and friendly for gradient methods, while the encoding length term places the golden network in a very hostile environment, at least for gradient-based methods. But this doesn't mean that a different kind of search wouldn't traverse this area better. So the question to ask at this point is whether we want to stay with such compromises that are visibly beneficial for gradient-based methods, or whether we want to invest some research in optimizing this kind of losses that bring us to these optimal networks, but are currently very hostile to current methods. So this is pretty much it. We're currently working on some exciting new directions to the project. We added some more expressivity to the different architectures that we can represent. So we added support for kernels, so we can represent convolution networks, and also all kinds of restrictions on the architectures that make it possible to represent bottlenecks. So we can create, for example, autoencoders. And we're also working on thinking of better optimization techniques for the MDL score. So once again, if there's one takeaway from this talk, is that information finds a way. And we believe that MDL is the most natural objective in order to prevent it from finding its way. So I'll stop here and I'll take questions.